Alright, what we have here is an open claw of a spider crab, and you can see inside there is a tendon, ligament, that goes to the large muscle, does the ducting, and you see how that moves when I close the claw? In fact, it pulls back somewhat, a little bit. Now on the top there, you can see the little ligament. That's what pulls and opens it, because there's a pivot right here. And so, when that one pulls back, it opens. And then you can see it when it closes, that one pulls up and in. And if I turn it a little bit, maybe you can see it. See right in there. So, that's basically the mechanics. All the muscles always pull. It has to pull on top and on bottom. The larger one, to pull it closed, is bigger than the smaller one, which moves very slowly. And then if we dissect it, you can see them more clearly. There and there. And that's the pivot hinge. Now from here to here, and then from here to the tip, if you divide those two distances, that's how you can figure out the mechanical disadvantage, actually, of the claw, because the claw is not meant to magnify the force, it's meant to magnify the speed. The force is always lost because the lever arm that's doing the pulling is smaller. So it's an interesting thing. It's often presented in the books as a mechanical advantage, but really it's not to the advantage. If it really were true that these things were evolving this way, it sort of seems that this lever should be longer to generate more force, especially considering that they're used to crack open hard-shelled things, but there's sort of a balance of power that it doesn't go beyond that. In fact, the lever continues to get smaller as the animal grows, or it plateaus, and yet it's something that the animal really doesn't have to expend any energy to maintain the mechanical advantage. Something interesting to think about.